classification problem. So please, if I forget recording, no, please, some of you, please remind me. Okay, I have the tendency of forgetting. Fine. Yeah, the logistic regression model is basically for the classification task. Classification task. Okay. But the name, by looking at the name, we may get an impression that it is for the regression problem. It's actually not. It is for the classification problem. You will understand that why this name has come, right, as we proceed. Okay, so in this session, we're going to see what is the classification problem, and we'll also see the logistic regression solution for the classification problem. And then we'll also look at the intuition behind the objective function and gradient descent algorithm. So as I have mentioned, this logistic regression model is basically for the two-class classification problem. It means binary classification problem. So we will see how to extend the solution to the multi-class classification problem. So this is the agenda for, please give me a second. We'll see how to extend it to the multi-class classification problem. All right, so this is the agenda for today. So first we will see what is a classification problem. All of you have idea about it, right? So what is the type of target variable in the case of classification problem?
Discrete.
Discrete, yes. So we have given input output pairs x1, y1, x2, y2, so on, xm, ym, and given a new instance for which we know only the feature vector, but we don't know what is the corresponding class label. So we have to pick up one of the existing classes as a prediction for this new instance. So this is a classification problem. Now the question coming in is that why can't we take a regression model for a classification task? Let's say linear regression. Why can't we apply linear regression model to this classification task? Okay, so let us take an example and try to understand this. So for this, I am taking an example of whether a person buys a computer or not, right? This is the target variable that I'm interested to predict. If a person buys a computer, then the output is 1. If the person doesn't buy a computer, then output is equivalent to 0. There are two classes, two-class classification problem. And the feature based on which we are making this prediction is age of a person. So the X is the age of a person, feature input variable is age of the person, and the output variable is whether a person buys a computer or not. Okay, so if person buys a computer, then it is a 1, otherwise it is a 0. So let's say different ages, 15, 20, 25, 30, 35, 40, 45, 50, 55, and so on. All right, something like this. Let the data given to be like this. Given to us is something like this. All these are the positive instances where the person buys a computer, and all these are the negative instances where the person doesn't buy a computer, right? So these are all the negative instances and these are all the positive instances, right? So now what happens if I fit a regression line to this data? I'll get a line something like this. Agree? Am I right? If I try to fit a linear regression model to this data, I may get some line like this. Okay.
Yes.
So now if I want to make a prediction for the new data, let's say there is a person with age 70 somewhere here. Okay. So what is the prediction that it is making? It would be around somewhere around -1. So buys computer equivalent to -1. This is what the output it is giving. Does it make any sense? Buys computer equivalent to minus is not making any sense, right? Right. So one of the problem is that how do you interpret it? You see that the regression is making the prediction of the values in the range of -infinity to infinity. It can be any value because it's a continuous and it can take any value. Whereas this output we are expecting in the range within the two values 0 or 1, right? So the two possible class labels. So one can say that what is so great about it, sir? We can easily sort it out. I would say that anything greater than 0.5, just make it as a 1. Anything less than 0.5, just round it off to 0. Right? That can be done, right? So if you get any value greater than 0.5, just round it off to 1. If you get any value less than 0.5, just round it off to 0. Right? I mean, make it 0. Right? That possibility is there. Even then, there are other problems with this logistic regression. I mean, applying linear regression model to this classification task. Okay, let us see that. Suppose there is an imbalanced data set. Like say, let's say that there are few more instances, few more negative instances, something like this. Like where a person buys a computer or not, right? So now if you see this, there is more number of data points on the negative side of this, more number of negative instances and less number of positive instances. And what the linear regression model is doing, it is trying to fit a model such that the difference between actual and the predicted instances is minimized, isn't it? So if there are more number of instances this side, the line will be biased towards this, something like this. Hello, am I right? So if you set a threshold of 0.5 here, you see that threshold of 0 point is somewhere here. It means anything above this, you're classifying it as a positive instance, right? So as a result, all these instances will be misclassified, right? So do you understand the problem? Do you understand the problem? Or should I give another example? Hello? Nobody is talking? Not following?
Sir, please give another example.
Another example, class imbalance. Let's say that there are, all these are the positive instances, y equivalent to 1. And let's say that very few instances are from class 0. Okay, 2, 3 instances are. If you try to fit a linear regression model to this, what is the goal of the linear regression model? It is trying to fit a line so that the difference between actual and the predicted values is minimized. On an average, I mean, on the whole, it has to minimize the overall error, isn't it? So in that process of minimizing the overall error, the line will be biased towards the class with the more number of instances. Am I right? Because there are very few instances. If you count the error with respect to these few instances, this is very less, right? So it means the error of this line is much lesser than error of this line. Agree? Because yes, because this, all these points are more close to this line rather than this line, right? Says there are very few instances in the other class, it is more biased towards the class with the more number of instances. As a result, what happens if you want to make a prediction for the new instance? So every point will be predicted as the one only, right? Because the line is going through this. Am I right? Wherever the point is, whether it is here or here or here, or it is predicting it as a y equivalent to 1. It means this class is completely ignored. It means that it is what do you say, that it is misclassifying all these instances, right? It means the class is more biased towards the class with the more number of instances. I mean, the algorithm is more biased to the class with the more number of instances. Do you understand the problem of applying linear regression model to the classification task? Is that point clear? Why don't we apply
Yes, sir. Yes, sir.
linear regression model to the classification task? Okay, great. So all right, so if we cannot apply linear regression model, then what is the model? What is the representation of the hypothesis that the logistic regression model is giving? So first of all, it gives the probability estimate of a class label y equivalent to 1. So it will not just give whether it is a 1 or 0. The hypothesis representation h theta of x is probability of y equivalent to 1. So this estimates the probability of y equivalent to 1. So if you know probability of y equivalent to 1, and it is also given to you that there are only two classes. So can you estimate what is the probability of y equivalent to 0? If you know probability of y equivalent to 1, what is the probability of y equivalent to 0?
1 minus
One minus probability of y equivalent to 1, as there are only two classes. So which is 1 minus h theta of x. H theta of x is the hypothesis or the output that you are getting, the prediction value, right? So that's what this logistic regression model is giving. So it is a classification based on the probability. It means instead of just predicting the class, we give the probability of the instance being in that class. It means we are trying to learn probability of y for a given x. X is the input vector, input feature vector, right? So if you compare it with the linear regression model or the perceptron, thus does not produce the probability estimate. All right. So the linear regression model does not produce any probability estimate. Okay. So we want to learn a hypothesis such that a hypothesis is giving us probability of y equivalent to 1. Okay. So if you look at this line, the representation of the hypothesis representation is z of theta transpose x, where z is the sigmoid function. Okay, so don't worry if you're not following something. I will explain it. Don't worry about that. So in case of logistic regression model also, we have a line, but line here is not going through the data points. It is acting like a separating hyperplane that separates the positive instances from the negative instances. All right. So, but here the representation of the hypothesis is probability value, probability that a point belongs to a positive class, right? That means there should be some way to map this line representation or a hyperplane representation to the probability terms. Okay, so what is the line representation or a hyperplane representation? It is theta naught plus theta 1 x1 plus theta 2 x2 and so on, theta d xd, where d is the number of dimensions or the features, right? So in the vectorized notation, I can write it as a theta transpose x. This we have seen earlier.
Yes, correct.
This class. So this is a theta transpose x. So there should be some way to map this line to a probability. So to map this line equation to the probability, we are giving this to the sigmoid function. Sigmoid is indicated with either sigma or z, right? Z also sigmoid function, sigma also sigmoid function. So sigmoid of theta transpose x is 1 by 1 plus e to the power minus theta transpose x. So this maps the values in the range of 0 to 1, right? So when you give this theta transpose x, which can be in the range of minus infinity to infinity, this sigmoid function mapping the values in the range of 0 comma 1, right? Mapping the values in the range of 0 comma 1. It means it is transforming this line equation to the probability terms. So this is giving us the probability of y equivalent to 1. Once you get the probability of y equivalent to 1, you can estimate the probability of y equivalent to 0. Okay, so let me elaborate this so that you will get more idea about it. Okay, so a question to you now. Suppose if there is a new point, that you want to classify, and let's say that the point is somewhere here. So can you say that either it belongs to class 1 or class 0, positive class or negative class? Are you confident that whether it belongs to positive class or negative class if the point is on the line? We are not sure about it. Am I right?
Yes, sir.
Yes.
Because there is equal chance of belonging to either positive class or negative class, because it is exactly on the middle, it is on the line, right? So we are not sure about it. So what do you expect as the probability of y equivalent to 1 in this case? The line equation is theta transpose x, right? So if the point is on the line, it means the theta transpose x is equivalent to 0. So theta transpose x equivalent to 0. What is z of theta transpose x? Sigmoid of theta transpose x? 1 by 1 plus e to the power minus theta transpose x. What is the value of e? 2.71, which is the base of the natural logarithm, right? 1 by 1 plus 2.71 to the power 0. How much it is? 1 by 1 plus 1, which is 1 by 2. So probability of y equivalent to 1 is 0.5. Then what is the probability of y equivalent to 0?
0.5.
0.5, 1 minus 0.5, which is also 0.5. It means equal chance that it belongs to either class 1 or class 0 in this case. So let's say that there is a point somewhere here. Are you sure about this? To which class it should belong to?
Both the
If the point is somewhere here, it is on the positive side of the plane, isn't it? So there is a
Yes.
higher chance that it belongs to the positive class. Am I right?
Yes.
Right. So if theta transpose is somewhere here, this is only possible when this theta transpose x is a big positive number. So theta transpose x is a big positive number. Let's take it as a 10. Theta transpose x equivalent to 10. So what is z of 10? Z of 10, z of theta transpose x. Theta transpose x is 10. Z of 10 is 1 by 1 plus 2.71 to the power minus 10. What is the value of 2.71 to the power minus 10? 1 by 2.71 to the power 10. It means this is almost close to 0. Hello? Agree? 2.71 to the power 10. It's a very big number, right? So 1 by very big number is close to 0. Agree?
Yes, sir.
Right. So this I can write it as this is close to 1 by 1 plus 0, which means it is close to 1. Right. So if probability of y equivalent to 1 is close to 1, what is the probability of y equivalent to 0?
0.
0.
Close to 0.
0.
Right. That's what we are expecting, right? Right. So it means if the point is on the positive side of the plane and it is far away from the line, then our confidence in saying that it belongs to positive class is very much high, right? It's almost close to 1. We are almost sure that it belongs to the class 1. 99.9999% sure that it belongs to class 1. So I'm just giving you the interpretation of this hypothesis. I hope you're following that.
Yes, sir.
Yeah. So now let's say that there is a point somewhere here, which is on the negative side of the plane and it is also far away from the plane. Right. It means if it is here, it means what? It is a big negative number. It is much lesser than 0. Let's take it as a minus 10. What is z of minus 10? 1 by 1 plus 2.71 to the power minus of minus 10, which is plus 10. So what is 1 by 1 plus 2.71 to the power minus 10? This is almost close to 0. Hello? Agree?
Yes. Yes.
Right.
Yes.
So if this is close to 0, what is the probability of y equivalent to 0?
1.
This is close to 1. It means you are more confident that it belongs to the negative class or 0 class, class 0, right? This is what the interpretation that we are giving, right? So this is what the interpretation that we give to the cost function. All right. So the interpretation of the hypothesis, if you see, h theta of x is the estimated probability of y equivalent to 1. So if you take the cancer diagnosis from the tumor size, means we want to say whether the tumor is malignant or benign based on the tumor size, right? So here, if the hypothesis output is 0.7, it means that you are telling a patient that 70% chance of tumor being malignant and 30% chance of tumor being benign. All right. So if 0.3, if hypothesis is 0.3, then what is the interpretation? What you're telling to the patient? You're telling to the patient that 30%
30%.
30% chance of tumor being malignant and 70% chance of tumor being benign, right? So that is what the interpretation that we are giving to this cost function, this hypothesis. All right. I hope all of you are clear with the hypothesis interpretation. Got right? Have you got the interpretation of the hypothesis? How do we interpret the hypothesis of the logistic regression model? Is that clear? Any query? If you want me to repeat something also, I can do that. Please let me know. Is it clear? Geeta ma'am?
Yes. Yes, sir. Yes, sir. No, yesterday we have designed such a big hypothesis, no, sir. Taking all theta 0 plus theta 1x plus. Today it is not that big, is there? Fine. Understood. Sir.
All right. Snehalata ma'am, Ash. Everybody, is it okay?
Sir.
Yeah.
Okay, sir.
Yeah, Sanjay Kumar sir.
Yes, sir. Okay, sir.
Yeah. So there is another interpretation of this hypothesis. Okay, so let us try to understand that. Slightly difficult, but please pay attention so that you will understand it better. So another interpretation is that logistic regression assumes that log odds is the linear function of x. So let me go a bit slow because you're facing slightly difficulty, I think, to catch my speed. So let me go a little bit slow. This is another interpretation that we give to the logistic regression model. The logistic regression assumes that log odds is a linear function of x. So by looking at this statement, you may not be able to understand anything, but let me put it this way. So what is the we are saying the hypothesis representation is probability of y equivalent to 1. This is what the hypothesis is, h theta of x. Tell me the range of the probability values. Range of probability values. What values that it can take? Probability.
0 to 1.
0 to 1. So the range of probability values is 0 to 1. It means the output must be in the range of 0 to 1. So what happens if you take the directly line equation as the hypothesis? Suppose if I say h theta of x equal to theta transpose x, like in case of linear regression model. What happens? What are the possible values for this theta transpose x? What are the possible
Theta
values?
naught. Theta
Minus
naught.
infinity to infinity. No, I'm not asking about the parameters of this. What are the possible values for this theta transpose x?
Yes. Minus
This
infinity.
can be any value, right? Minus infinity to infinity. So this is why we cannot take directly the line equation as the hypothesis, right? So if you take directly line values, this gives the values in the range of minus infinity to infinity, whereas the output that you're expecting is in the range of 0 to 1, right? So it means there should be some way that you map this minus infinity to infinity to the range of 0 to 1, or 0 to 1 in the range of minus infinity to infinity. There should be some way that you map this 0 to infinity in the range of minus infinity to infinity, or minus infinity to infinity in the range of 0 to 1, right? So that's what this actually the logistic regression model is doing. It is trying to map this range of minus infinity to infinity in the range of 0 to 1. All right. So probability gives the values in the range of 0 to 1. Okay. So let us take an example. Suppose if I ask you what is the probability of die equivalent to 6, what is your answer? Die equivalent to 6.
1 by 6.
1 by
1
6.
by 6, 6 phase die, 1 by 6. Right. So this one is the weight corresponding to die equivalent to 6, and this is the overall weight, weight associated with each and every possible output, right? 1 by 6. Another question. If I ask you what is the odds of die equivalent to 6?
1 by
Odds.
2. 1 by 2.
1 by 2.
By 2? No. None. Odds definition is not that.
1 by 3, sir.
No, not that. There is a definition for the odds. Let me complete that. Okay. So the odds also giving the likelihood estimation of this die equivalent to 6 only. But only thing is that it is in the different scale than this probability. Okay. So suppose if I ask you odds in favor of some event. Okay. So odds of the event is equivalent to probability of the event divided by 1 minus probability of the event. This is the definition of the odds. So odds in the favor of an event is the quantity P by 1 minus P, where P is the probability of the event. So looking at this definition, can you now tell me what is the odds of die equivalent to 1 or die equivalent to 6?
1 by 5.
1 by 5. 1 by 6 divided by 1 minus 1 by 6, which is 5 by 6. So therefore, it is 1 by 5. Okay. So this is also giving the likelihood of die equivalent to 6. But the properties of this is slightly different from the probability. So the probability values are in the range of 0 to 1, no? But odds are in the range of 0 to infinity. This is the different property. So now instead of taking the probability, if I take odds of y equivalent to 1, then we can map this in the range of 0 to infinity. But still we are not there. What is the range of minus line theta transpose x? minus infinity to the infinity. Okay, whereas this 0, 1, this is in the range of 0 to infinity. So there should be some way to map the 0 to infinity to the range of minus infinity to infinity. Okay, so to map this 0 to infinity in the range of minus infinity to infinity, we can give it to the log function. Log function. Log of odds of probability of y equivalent to 1. Okay, so this is in the range of minus infinity to infinity. Right. So can you tell me what is the log odds of y equivalent to 1, probability of y equivalent to 1? Log of, what is the odds of probability of y equivalent to 1? Probability of y equivalent to 1 divided by 1 minus probability of y equivalent to 1. Yes or no? Right. So what is 1 minus probability of y equivalent to 1?
P of y equal to 0.
Y equivalent to 0. So this is log of probability of y equivalent to 1 divided by probability of y equivalent to 0. Okay. So this is equivalent to what? This is equivalent to theta transpose x. So now are they matching? Ranges are matching, right? This is in the range of minus infinity to infinity. What about this? What about this? This is also in the range of minus infinity to infinity. Am I right? So the characteristics are matching now. So this is what the assumption is. Okay. So the logistic regression assumes that log odds is a linear function of x. I'm not yet completed. I know that one point is missing, but I just want to check whether you could follow it or not till this point.
I think left hand side there is a log as an operator, isn't it? Hello?
Here, you're talking
Yeah,
about
yes.
this.
Sir,
Yes, yes.
why we are not applying? See, if you take log, so LHS, RHS, both the sides we have to apply the log. Why it
No,
is
no, no,
appearing
don't.
in one?
No,
So
no.
it's a
Please try to
formula.
understand this.
Okay.
See here, I'm just trying to give you inputs that why can't we take directly the line equation as the hypothesis representation? Right. What happens if you directly take, I mean, we have seen the intuitive way in the first slide itself. Okay, technical part, I'm just trying to talk about technical. Okay. See here, if you just directly say this, h theta of x is equivalent to theta transpose x, what is the interpretation that you're giving to the hypothesis? You are saying that this is the probability of y equivalent to 1. What is the range of probability values? 0, 1. Right. What is the range of this theta transpose x?
Minus
Minus
infinity to
infinity to
infinity.
infinity. Right. So you are one hand you are saying that you are giving the probability values. On the other hand, if you take this theta transpose x, that gives the values in the range of minus infinity to infinity. So the characteristics are not matching. Am I right?
Yes.
So there should be some way to map this minus infinity to infinity in the range of 0 to 1. Am I right? All right. So the other way also, you map the 0 to 1 in the range of minus infinity to infinity, reverse engineering, right? So both the ways you will be able to get the solution. So here we are trying to map the 0 to 1 in the range of minus infinity to infinity range. Till this point, is it clear, sir? Till this point, is it clear, sir?
Oh, okay, sir. Clear.
Yeah, clear. So now one step we are taking here, mapping this 0 to 1 range in the range of 0 to infinity. Okay, how are we doing this? Instead of taking the probability of y equivalent to 1, we are taking odds of y equivalent to 1. What is odds? Odds is p by 1 minus p. So if you take odds of y equivalent to 1, you will get probability of y equivalent to 1 divided by 1 minus probability of y equivalent to 1. Okay, it means you are giving this probability as an input for the odds function, right? So you have probability of y equivalent to 1. You are giving this to the odds function. Odds function, probability of y equivalent to 1. So when you give this 0, 1 range input to the odds function, this will transform this to the range of 0 to infinity. Clear till this point? So now you have succeeded half. You mapped 0 to 1 in the range of 0 to infinity. But what is your aim? You want to map it in the range of minus infinity to infinity.
Yes.
Hello, sir? Is it clear? Right. So now you give this output, whatever that you get from the odds, to the log function. So log will give you the values, the range of minus infinity to infinity. So this odds function, you're giving it to the log. This will return you the values in the range of minus infinity to infinity. Now, are these two characteristics matching? Log of odds of y equivalent to 1 and theta transpose x. Theta transpose x is in the range of minus infinity to infinity. Log of odds also in the range of minus infinity to infinity. Right? So are these two matching? Hello, sir?
Yes.
Yes. Now, let us try to derive this now. We have not yet completed. I just want to check whether you have followed so far or not. Followed? Is this clear? Everybody, please let me know. Because very less responses, I am in a doubt that whether you could follow it or not.
No, sir, it's clear.
Yeah. Okay. But Geeta madam, no. Snehalata madam, and
Sir,
Betty.
perfectly understood because you are revising it, no, so I kept it quiet, sir.
Okay, okay, fine. So now we know that log of probability of y equivalent to 1 divided by 1 minus probability of y equivalent to 1 is equivalent to theta transpose x, which is this theta naught plus theta 1 x1 plus so on theta dx, theta transpose x. So can I apply exponential term on both the sides?
Yes.
E to the power log, okay, okay, what is that, log probability of y equivalent to 1 divided by 1 minus probability of y, e to the power theta transpose x. This is exponential, this is exponential, right? So this can be written as directly log probability of y equivalent to 1 divided by 1 minus, sorry, log and e gets cancelled, sorry. So probability of y equivalent to 1, 1 minus probability of y equivalent to 1 is e to the power theta transpose x. So if you derive what is the probability of y equivalent to from this equation, you will get 1 by 1 plus e to the power minus theta transpose. So this is how you got this hypothesis, 1 by 1 plus e to the power theta transpose x. This is the representation of the hypothesis h theta of x. Got it, right? Clear, right? The interpretation of this?
Yes, sir.
How we got this h theta of x? We are just mapping this minus infinity to infinity in the range of 0 to 1 using the sigmoid function. That's the, if you don't understand the whole derivation also, just understand this point. So that point is clear, right? How we are mapping this line equation to the range of probabilities 0 to 1. Clear? That interpretation is clear, right? Shall we move on?
Yes, sir.
Yes.
Yes, sir.
Okay. Okay. Fine. So now you look at this example again. So this was the example, right? These are all y equivalent to 1. These are all y equivalent to 0. Okay. So please answer to this question. Okay. So suppose I said that we are learning a separating hyperplane so that the positive instances are separated from the negative instances. All right. So you see this, there are, I'm giving you multiple options, right? You see this line, is this separating positive instances from the negative instances? Separating, right? Line 1. Line 2, this is also separating, am I right?
Yes, sir. Yes, sir.
This is also separating. Line 3, this is also separating. So which one of this is, do you think is the better?
L3.
Line 3 is better, why? All of them are separating accurately. Why line 3 is better than line 1 and line 2?
To play safely, sir, we should go with the line 3 only. Loss will be less for the line. Yes, yes, that's what.
Amount of separation is better in L3.
Great. So thank you very much for your responses. All of them are correct, and I'm happy to listen to these many responses also. But let me put at another view of it. Okay. So when you are learning a line, you want to learn a line in such a way that you want, you are confident about the prediction of most of the instances, or you want to be confident about the prediction of very few instances.
Confident about most of the instances.
Confident about the prediction of most of the instances, right? We want to learn a line in such a way that we are confident about the prediction of most of the instances, right? Suppose if you learn a line which is close to these instances, okay, close to this y equivalent to 1 instances, is it confident about the prediction of these points? Do you remember? Do you remember this? When theta transpose x, what was this hypothesis? Equal to 0. What is the hypothesis? H theta of theta transpose x? 1 by 1 plus e to the power 0. This is 0.5. It means probability of y equivalent to 1, probability of y equivalent to 0, 0.5. Okay. So if it is somewhere here, it may be 0.55 or something like that. It means what? You are saying that 55% chance that it belongs to class 1 and 45% chance that it belongs to class 0. Right? Not that confident, right? So suppose if this theta transpose x, if the point is far away from the line and it is on the positive side of the plane, it means what? This theta transpose x is a big positive number. I took it as a 10 earlier, right? So if this is 10, what would be this hypothesis output? E to the power minus 10, and this is close to 1, some 0.99, let's say. It means what? Your 95% confidence that this point belongs to class 1 and only some 0.01 probability that it belongs to class 0, right? So which one of these lines will be more confident about all the training instances prediction? If you learn this line, this is more close to the positive instances. It means what? This is not more confident about these points because they're close to this line, and it is more confident about this line, these points. Am I right? Hello, following it?
Yes, sir.
No?
Yes.
Following, or should I repeat?
Yes, sir.
Yes, following. Okay. Suppose if I learn this line, is it confident about all these points? It is less confident about these points, right? As they are close to this line, right? Probability values corresponding to them is very low, right? So, but if I learn this line, what does it means? This is far away from both the sides. It means it is confident about all the points in the training data. Am I right? Hello?
Yes.
Right. So we want to learn this line in such a way that the model is confident about the prediction of most of the training data points, right? That's what the intuition behind this. Okay. So if it has to be confident about most of the points, this line should be far away from both the sides, right? This line should be far away from both the sides. So we are learning this line in such a way that we are learning this line theta transpose x in such a way that theta transpose x should be a big positive number for all the positive instances in the training data, and this theta transpose x should be a big negative number for all the training instances, isn't it? So that's what it is doing here. So we have to learn this theta transpose x in such a way that it should be a large positive value for all the positive instances, and it should be a large negative value for all the negative instances. So I hope you understood why is that we have to do this. Understood, right?
Yes,
Sir.
sir.
Yes, sir.
Right. All right. So now, how to do this? How to do this? So imagine that I made all of the participants into two groups and I allotted one Nekara space to all of you. And I said, fix a wall such that anything left of this wall is assigned to the group 1, anything right of this wall is assigned to group 2. Right? So how do you push this wall? Equally strongly from both the sides, isn't it? How will you fix this line between, so the group 1 will be pushing to one side and group 2 will be pushing to the other side. Finally, you will fix it at somewhere at the middle. Am I right? Hello?
Yes, sir.
Right. So similarly here, these all points will push this line towards this side and all these points will push this line towards the other side. So somewhere in between it will be fixed. Right. So of course there is one problem also. Suppose there is a class imbalance problem. Class imbalance problem. It means let's say that more points are this side and very few points are this side. Then the strength of this will be more. It means all these points may be pushing this line more towards this line. It means the line is more biased to these points and it will be close to these points. Okay. Because our objective is to minimize the overall error. Right. That possibility is there if there is a class imbalance problem. All right, fine. All right. So I hope so far you're with me.
Yes, sir.
Yeah. So now, if so far we have assumed that the data is linearly separable, and we are trying to fix a line so that it separates the positive instances from the negative instances, such that the line is far away from both the sides. Okay. What if the data is not linearly separable, like the one that you can see in this figure? So can you draw a line that separates these green points from the red points? Is that possible? It's not
Line.
possible to draw a
Yes.
line that separates the green points from the red points, right? So that means this data is not linearly separable. There is no linear separation between the instances of both the classes, right? So in this case, what we do is that we apply a basis function, right? Huh, madam?
No, sir. Pen I was asking.
Okay, okay. So basis function, in a sense that you remember what we have done in the case of polynomial regression model.
Yes, sir.
We are generating additional features like polynomial features, x1 square, x2 square, x1, x2, x1 cube, x2 cube, so on, something like this, polynomial features.
Is it manually crafted features or it is going to be automatic?
No, this, I mean, manual, which one? Manually crafted features.
This one.
Are you talking about these features?
No.
This one. This one,
Mapped.
you are applying some function, sir. What kind of features that you get is depending on the function that you apply. Okay. So here, if you apply the polynomial features, polynomial function, then you may get features something like this. Okay. So yeah, these are manually generated only. To answer to your question straihtly. Only thing is that you are giving it to some function. So that function is generating these features.
But for first one, like one x1, x2, we are fixing that one, and third one x1, x2, we are actually having that like that.
See, it is like this.
Okay.
So you are transforming the problem to some higher dimensional space so that there exists a linear separation between them. I can give you one example so that it will be more clear to you. So let's take a data set of one-dimensional data. And let's say that the data is something like this. Let's say this is 0, 0, 0. So let's say there are some positive points here. Okay, and there are some positive points here. Positive points here. And there are, I mean, positive points means y equivalent to 1. Cross mark is y equivalent to 1. Circle is y equivalent to 0. And this is 0, value 0. Okay, at this point. So this is how the data set looks like, one-dimensional space. Is this data linearly separable?
No, no.
Not separable, right? If you draw this line, all this will be misclassified. If you draw this line, all this will be misclassified. There is no linear separation. Okay. So this is X. Let us now expand it to the two-dimensional space by adding an additional feature, X squared. Okay. So now I said this is 0, right? So 0 square is 0. So this point will be somewhere here. So these points, these are negative points. All these are the negative points. Let's say this is -1, -2, something like this. This is +1, +2, something like this. 0.5, -0.5, something like this. Okay. So now the moment when you add a two-dimensional space, so this will become, let me redraw this. It will become like this because X square for the negative numbers also positive. Hello, am I right, sir?
Yeah, yes, sir. Yes, sir.
Yes. So now in the two-dimensional space, is it linearly separable?
Oh,
You can draw a line that separates circles from the cross marks. Am I right? In the two-dimensional space?
Yes.
Right. So this is not linearly separable in the one-dimensional space, but the moment you are transforming the problem to some higher dimensional space, there exists a linear separation between the positive and the negative instances, so that you can draw a line or a hyperplane to separate them. It means what? You're transforming the problem to some space where there exists a linear separation, and then applying this logistic regression model. So this looks like a linear model in the higher dimensional space. But the moment when you express it in terms of the original set of features, this is non-linear only. This is the boundary that you're creating, in fact, right? So the moment you express it in terms of the original data points, the model is non-linear. So the model is linear in the case of new representation, but it is non-linear in the world representation. Right?
Yes, sir.
Similarly, here this may be non-linear boundary in the two-dimensional space, but the moment you extend the problem to some higher dimensional space, there is some hyperplane that separates the positive instances from the negative instances. So that in the new space it may be linear, but the moment when you express it in terms of the world representation or the original data space, this looks non-linear only, as you see in this figure. Clear, sir?
Yes, sir.
Yeah. Yeah. So this is how we solve the nonlinear cases. We transform the problem to some higher dimensional space and apply logistic regression model. Okay. So to summarize whatever that we have discussed so far, there are some notational confusions. Please don't mind that. So here n is used for the number of instances. Previous slides we have used m. Okay. But throughout we have used d for the number of dimensions. Okay, don't confuse that. Okay, so given x1, y1, x2, y2, so on, xn, yn, xi is the d-dimensional feature vector, yi is belong to 0 or 1. Right, this is the problem to predict for the new instance xn plus y for I greater than or equal to 1. So the hypothesis representation is g of theta transpose x, which is equivalent to 1 by 1 plus e to the power minus theta transpose x, where theta is the d plus 1 dimensional parameter vector and x is the d plus 1 dimensional feature vector, right? One dimension is only one, which is x naught. Okay, so till now you could follow, isn't it? Any query? Could you follow so far? Are you with me?
Yes, sir.
Yes, sir. Yes, sir.
Now we are clear with the hypothesis. Okay, what else we need? We need a loss function, right, to learn the optimal parameters. What was the loss function in case of linear regression model?
Theta minus y.
H theta of x minus yi whole square, right? Sum over I equal to 1 to m h theta of xi minus yi whole square. 1 by 2m sum over I equal to 1 to n 1 to m h theta of xi minus yi whole square, right? It means squared loss we took. Okay, a question to you. So can we take the squared loss as a loss function in the case of logistic regression model also? Could you follow the question? Did you understand the question? Can we apply the squared loss in case of logistic regression model also? Right. So we cannot use the squared loss in case of logistic regression model as in case of linear regression model. Okay. So we can't use this squared loss. What is the reason? The hypothesis representation now is the probability, right? And yi value is either 0 or 1. Okay. What is there? That anyhow the probability values are in the range of 0 to 1 only. Why not we apply squared loss? Right. The problem is that with this representation of the hypothesis, if you go for the squared loss function, it will result in non-convex optimization. It will result in non-convex optimization. With this hypothesis representation, if you apply squared loss function, then it will result in non-convex optimization. What do we mean by non-convex optimization? And what do we mean by convex optimization? So in the convex optimization, the problem looks something like this, wherein we have only one local minimum and that is equivalent to the global minimum. Whereas in case of non-convex optimization, you may have multiple local minimums and the local minimum may not be equivalent to the global minimum. So as a result, there is a higher chance that your solution will stuck up in the local minimum and it is difficult to solve the problems with the non-convex optimization. Alright, so we use the meta heuristic functions or the soft computing techniques to solve these non-convex optimization problems. Alright, so do you understand why we cannot apply the squared loss function for the logistic
Yes,
regression model? Right,
because we are not, because of this. Now we
Non-convex.
understood, sir, because of the representation of the graphs.
Okay, okay. So it will result in non-convex optimization and it is difficult to solve the non-convex optimization problem. So better to avoid that, right? If there is a chance. Otherwise, you can go with the some soft computing techniques like the PSO and B colony and colony optimization. You might have heard of these algorithms, right? So you can go for the such algorithms, particle sum optimization, genetic algorithms. All this is to solve those kind of problems. All right. So anyhow, that's not the theme of our FDP. We are not going to that direction. But now, if we cannot apply squared loss, what loss function should we apply? We cannot apply the squared loss function. What loss should we apply? Okay. Let us try to derive it from the probability concept of view, probabilistic interpretation, right? Like the way that we have derived it from the linear regression model in yesterday's class, in day before yesterday's, or yesterday only, right? Okay, yes, no, day before. Okay.
Yesterday polynomial regression.
Yesterday polynomial. Day before we have derived that. Do you remember? We have derived this loss function from the probability terms, right? Maximum likelihood estimation. All right. Similar way, we will derive the loss function for the logistic regression model also. Okay. So we'll derive the cost function via maximum likelihood estimation. Okay. So slightly difficult. I want you to pay the attention. Okay. So here we want to maximize the likelihood of the data. It means we want to learn theta that maximizes the likelihood of the data. We want to learn theta that maximizes the likelihood of the data. All right. So please keep that in mind. So the data given to us looks something like this. We have given x1, y1, x2, y2, x3, y3, and so on, xn, yn. This is what is given to us. And this y1 or yi can be either 0 or 1. Each yi can be either it is 0 or 1. Let's say y1 equivalent to 1, y2 equivalent to 0, y3 equivalent to some 1, and y4 equivalent to some 1, and so on, yn equal to some 0. Okay. All right. So when we are saying this, we want to maximize the likelihood of the data. What do we mean by that? We want to maximize the probability that yi belongs to a certain class given the corresponding xi. It means I just want to maximize probability of y1 equivalent to 1 whenever x1 is given to me, because the output is 1 only, right? Similarly, whenever x2 is given to me, I want to maximize the probability that y2 equivalent to 0 whenever x2 is given to me. Similarly, can you tell me what should I maximize? Probability of y3 equal to 1 or y3 equal to 0? What should I maximize when x3 is given to me? What should I maximize?
1.
1.
Y3 equivalent to 1. Similarly, for y4, what should I maximize?
1.
Y4 equivalent to 1. For yn, what should I maximize when xn is given to me?
0.
Equal to 0.
Probability of yn equal to 0 whenever xn is given to me, right? So precisely, we want to maximize probability of yi, whether it is 0 or 1, yi can be either 0 or 1, whenever the corresponding xi is given to me. So this is what I want to maximize for the individual instances, right? So this is the probability of one instance. Suppose if you want to get the probability of the whole data set, assuming that the instances are independently and identically distributed, IID fashion, right? So if they are independent of one another, so what is the probability of joint probability of y1, y2, so on, yn?
Multiplication of all the
Multiplication of all the probabilities. Probability of y1 given x1 and theta times probability of y2 given x2 and theta, and so on, probability of yn given xn and theta. So this is the likelihood of the data. So we want to learn this theta in such a way that it maximizes the likelihood of the data. It means product over all the individual probabilities. So learn theta that maximizes the likelihood of the data. So it means we want to learn theta in such a way that it maximizes this quantity. All right. So that is what is the objective is. So our objective is to learn theta that maximizes the likelihood of this data. Right. Fine. So far good. Could you follow so far? Are you with me?
Yes, sir.
Yes.
Yes. So
Yes,
now
sir.
maximizing some function f of x is equivalent to maximizing log of f of x. Agree? Yesterday also, day before also we have seen. Maximizing f of x is equivalent to maximizing log of f of x as they are proportional to one another. Okay. So instead of taking this function directly, we took the log of it. Why? To simplify the mathematics. No other reason, right? So we took log of f of x, log of this. So using this formula, log of a times b is equivalent to log a plus log b. This you know, right? So when you expand this log function over the product terms, then you get the sum over log of probability of yi given xi and theta. So you want to select theta that maximizes this one. Sum over log probability of yi given xi theta. Clear so far? Hello? Is it clear? Is these two steps
Yes,
clear?
sir. Yes.
Right. Yeah. So now this is what we have seen in the previous slide. Now I am claiming that this is equivalent to this. Okay. It is slightly difficult for you to understand if I expand this and got this, but let us try to prove it in different ways. Okay. I just have to prove that this is equivalent to this. All right. Let me choose this way. What are the possible values for yi?
0 and 1.
0 or 1. These are the two possible values for yi. So let us take yi equivalent to 0 and substitute in this equation. When you take yi equivalent to 0, what will you get? 0 times log of this one, which is 0. It means the whole term is 0. Agree? Because yi is 0, 0 multiplied by anything is 0. So the whole thing is 0. So 1 minus 0 log 1 minus probability of yi equivalent to 1 given xi and theta. Right? So it means I got this. This is equivalent to log of probability of yi equivalent to 0 given xi and theta. Because 1 minus yi equivalent to 1 is yi equivalent to 0. Hello, correct?
Yes, sir.
Yes. So now, what is the yi value? 0 only, right?
0.
So I
0.
can directly write it as a log probability of yi given xi and theta. Isn't it the same?
Yes.
This one is the same. Now take yi equivalent to 1. Yi equivalent to 1. When yi equivalent to 1, what is this term? Log probability of yi equivalent to 1 given xi and theta. Plus, what is this term when yi equivalent to 1? 1 minus 1, 0. 0
0.
times anything is 0. So what you got? You got log probability of yi equivalent to 1 given xi and theta. What is the yi value? 1. So I can write this as a log probability of yi given xi and theta. Isn't it the same?
Yes.
Right. So it is just expanded for the two possible values, 0 and 1. That's all. Okay. So maximizing some function f of x is equivalent to minimizing minus f of x. Agree or no? Maximizing f of x is equivalent to minimizing minus f of x.
Agree, sir.
Agree? True? So here you took minus and converted this as a minimization problem. So we want to choose theta that minimizes this. This is the cost function. We call it as a cross entropy loss. Right. So far, are you with me? We have derived the cost function. We know what is the hypothesis, 1 by 1 plus e to the power minus theta transpose x. Now we have derived the cost function. Clear? Shall we move on? Or exhausted?
This topic was third topic in the slide.
Not exactly. Okay, I mean, as compared to the coming sessions, I think it's
Because when you have shown now that these are the points we will be discussing, I have seen it was third or fourth intuition behind them.
yeah, a lot of intuition. That one, I mean, it is good to understand all that intuitions instead of just discussing that this is the hypothesis, this is the way that you learn theta, that's all. Instead of that, it is better to understand all these intuitions, right, behind the cost function. Why this?
And motivate us.
Yeah. But you could understand it, right? I know that is little difficult to observe at a time. You go through it one more, two more times, then you will be able to observe. But are you understanding? That's the more important.
Yes, sir.
Yeah.
Yes, sir. Clearly.
Okay. Yeah. If you understand, it's no problem. Please go through it one or two times more through the slides. Then you will understand. You will absorb it. So now, all right, we have derived the cost function. And what is the intuition behind the cost function? I think today also it will become 8 or 740. No issue. Okay. The point is that you have to understand. I'll be happy spending more time, but you have to understand. Now tell me, we have derived the cost function, but what is the intuition behind it? What should be the intuition behind any cost function? We have seen the squared loss. What,
Minimum.
when the actual value and the predicted value are same, it should return a zero cost. The more the prediction is deviating from the actual value, it should return more cost. Isn't it? It should penalize more. It means the cost or the loss that we are adding to the cost function is more if the prediction is deviating more from the actual value, isn't it? That's what that should be the intuition behind any cost function. Even if the squared laws also we have seen, when the prediction equal to 1, actual value equal to 1, what is the cost that the squared loss is adding? 1 minus 1 whole square, which is 0. When the prediction is 2, actual value is 1. How much cost you're adding?
1.
1. When the prediction is 3, actual value is 1. Then you're adding a
4.
penalty of 4.
4.
Right? So it means the more the prediction is deviating from the actual value, the more penalty you're adding to the cost function, right? And that should be the intuition behind any cost function. So let us see what is the intuition behind this cost function. So look at this cost function and tell me, when yi equivalent to 0, how much penalty you're adding to the cost function? How much penalty you're adding to the cost function when yi equivalent to 0? Substitute yi equivalent to 0, how much you will get? This part becomes 0. This is 1. 1 time log 1 minus h theta of xi. There is a minus sign here. It means you're adding a penalty of minus log 1 minus h theta of x, isn't it?
Yes,
This
sir.
much penalty you're adding. Similarly, yi equivalent to 1. How much penalty you're adding? yi equivalent to 1, this part becomes 0 minus log h theta of xi. This much penalty you're adding when y equivalent to 1, right? So when y equivalent to 1, you're adding a penalty of minus log h theta of x. When y equivalent to 0, you're adding a penalty of minus log 1 minus h theta of x. All right. So now let us see this. Let me give you different examples and ask you a question. If yi equivalent to 1 and h theta of x equivalent to 1, is the prediction correct or wrong? H theta of x means probability of y equivalent to 1. Y equivalent to 1, it means the actual label is 1 and your prediction is saying that I'm 100% confident that it belongs to class 1. Is the prediction right or wrong? I'm asking a question.
Yes, sir.
Right.
Obviously it is right, right? 100% correct. How much penalty we should add in this case?
0.
0.
0 penalty. How much penalty this cost function is adding when y equivalent to 1? Minus log h theta of x. And what is the h theta of x value? 1. It means it is adding a penalty of minus log 1. And log 1 value is the plot of log z. 0, right? So log 1 value is 0. It is adding a penalty of 0. 0 penalty it is adding. So now another question. Y equivalent to 0 and h theta of x is 0. It means probability of y equivalent to 1 is 0. If probability of y equivalent to 1 is 0, what is the probability of y equivalent to 0?
Again log 1 minus log 1, that is equal to 0.
Yeah. And so, yeah, you're adding a penalty of minus log 1 minus h theta of x. Minus log 1 minus h theta of x means h theta of
Log
x
1.
is 0. Minus log 1 minus 0, which is log 1. So log 1 is 0 penalty. So this is also correct prediction. You're adding a penalty of 0 in this case also. Let me take a different case. Y equivalent to 1 and h theta of x is 0.3. Let's see. It means probability of y equivalent to 1 is 0.3. Is the prediction correct or wrong? Your actual label is 1. Your prediction saying that 30% confident that it belongs to class 1 and 70% confident that it belongs to class 0. Prediction
One
correct?
penalty need to be imposed more.
Some penalty
log
need to be
0.3.
added because the prediction is wrong. Am I right? So the actual label is 1. Your prediction saying that I am only 30% confident that it belongs to class 1. More inclined towards the other class, right? It means the prediction is wrong. So you need to add some penalty, positive penalty to the cost function. How much penalty you are adding when y equivalent to 1?
Log
Minus log of h
0.3.
of h theta of x.
Minus log h theta of x value here is 0.3.
0.3.
So 0.3 somewhere here, right? 0.3 0.3, it would be around minus 0.6 or 0.5. I'm not sure about this value exactly, but it would be around minus 0.5. Right, so minus of minus 0.5, 0.6, whatever, it doesn't matter for us. So you're adding this much penalty, plus 0.5 or 0.6. Some positive penalty you're adding. Okay, one more example. Y equivalent to 1 and h theta of x is 0.2. Is the prediction right or wrong? But
Wrong
actual value
prediction.
is 1 and a prediction saying I'm only 20% confident that it belongs to class 1. It means it is even more deviating as compared to the previous case. Am I right?
Yes. Yes, sir.
Earlier you are saying at least it is 30% confident. Now you are saying only 20% confident. It is even more deviating. It means you need to add even more penalty. Am I right? So how much penalty we add in this case? Minus log 0.2. And what is log 0.2? It would be around some minus 0.8 or 0.75. So minus of minus 0.8, 0.8 penalty you are adding. So now let us deviate it more. Y equivalent to 1 and h theta of x is 0.1. It is even more deviating, right? Earlier it is 30% confident, later it is 20% confident, now it is only 10% confident about the correct prediction. It is even more deviating. It means it has to add even more penalty. So minus log 0.1. So 0.1, it would be around minus 1. So minus of minus 1, which is plus 1. See that as the prediction deviating more from the actual value, you are adding more penalty to the cost function, right? So it is increasing. The penalty is increasing as the prediction is deviating more from the actual value. All right. So that is the intuition behind this objective function. So is this point clear? What is the intuition behind the objective function?
Yes, sir.
Yes, sir.
Yes. So when y equivalent to 1 and h theta of x is equivalent to 1, then the cost or the penalty is 0. As h theta of x is moving towards 0, the cost is moving towards this infinity. As h theta of x tends towards 0, cost is tending towards the infinity. Similarly, when y equivalent to 0 and h theta of x equivalent to 0, you're adding a 0 penalty. As h theta of x tends towards 1, your cost function tends towards the infinity. That's the intuition behind this objective function. So similar to this linear regression model, here also you can add a regularization term similar to the way we have added in the polynomial regression or the linear regression models. All right. So the gradient descent algorithm also same as in case of linear regression model. Same, initialize theta values, update them, theta j equivalent to theta j minus alpha times the derivative of j with respect to theta j. But here the cost function is different, hypothesis representation is also different. According to this cost function, you have to compute the gradient. It turns out that the updation rules are similar as in case of the linear regression model, right? But the hypothesis representation is definitely different. So there the representation is just theta transpose x. Here the representation is z of theta transpose x. That is different. Okay. So now we'll see. I hope you followed it so far. The previous few slides. Should I repeat? Followed. Gradient descent algorithm. Clear, right?
Yes, sir.
Yeah. So simple. There also you are doing that. Then theta j equivalent to theta j minus alpha times the derivative of j with respect to theta j. Here also is the same, right? Only thing is j is changing here. You have to compute with respect to this, and hypothesis representation also changing. All right. So now, fine. So far, if I have to summarize this, you're discussing about the logistic regression model. What is the hypothesis representation for the logistic regression model? 1 by
1 by
1
1 plus e to
1
the
plus e to the power minus theta transpose x,
Yes.
which is giving the estimate of probability of y equivalent to 1. And this theta transpose x is a line or a hyperplane equation that we are transforming it into range of 0 to 1 by applying the sigmoid function 1 by 1 plus e to the power minus theta transpose x. So all right, hypothesis representation is clear. Then what is the cost function? Can we apply the squared laws? Can we apply the squared laws for the logistic regression model? Can we apply squared laws for the logistic regression model?
No, sir.
No. Why? It will result in non-convex optimization. So what is the alternative? We are deriving it through maximum likelihood estimate. So it means we are deriving theta that maximizes the likelihood of the data. And when we derive it, we got this cross entropy loss. And we understood the intuition behind it. What is the intuition behind it? The more the prediction is deviating from the actual value, the more penalty it is adding to the cost function. That's the intuition behind this loss function. All right. So then we got the hypothesis representation and the cost function that asks us to learn the optimal parameters. So what algorithm we use for this optimal parameter learning? Gradient descent algorithm, which means it is updating values based on the gradient theta j equivalent to theta j minus alpha times the derivative of j with respect to theta j. All right. So that's all we have discussed so far. Now this is essentially for the two-class classification problem. How to extend it to the multi-class classification problem is the question. All right. So what is multi-class classification problem? First of all, if there are more than two classes, we call it as a multi-class classification problem. If there are more than two classes, we call it as a multi-class classification problem. And there are lots of applications of multi-class classification problem, like disease diagnosis, object recognition, or the character recognition, or digit recognition. All these are the examples of the multi-class classification problem. So we'll see how to extend it to the multi-class classification problem. But before that, you need to answer few questions. Okay. So what is the probability of die equivalent to 6?
1 by 6.
1 by 6. How did we get this? In the numerator, we have a weight associated with die equivalent to 6. In the denominator, we have the sum over all the possible outcomes, weight of all the possible outcomes, isn't it? That's how we got this 1 by 6, right? Okay. So now, what is the h theta of x for the logistic regression model? Probability of y equivalent to 1. What is it? 1 by 1 plus e to the power minus theta transpose x, isn't it? Okay. So now, what is this 1 by 1 plus 1 by e to the power theta transpose x? And this can be written as e to the power theta transpose x divided by 1 plus e to the power theta transpose x. Can I write this way?
Yes, sir.
Right.
Yes, sir.
Probability of y equivalent to 1 is e to the power theta transpose x divided by 1 plus e to the power theta transpose x. When you get the probability value of die equivalent to 6, probability of die equivalent to 6, you got 1 by 6, where the numerator is weight associated with die equivalent to 6 divided by sum over the weight associated with all the possible outcomes. So if you interpret this also in the same way, what is the numerator? Probability of y equivalent to 1 is this e to the transpose, e to the power theta transpose x is the weight associated with y equivalent to 1, and this one is the weight associated with y equivalent to 0. Can I interpret that way using the same in the similar lines?
Yes.
Right.
Yes, sir. Yes.
So now this is the interpretation that we give to the two-class problem, wherein we have one line that separates the positive instances from the negative instances, which is characterized by one theta vector theta. So now if you have multiple classes, we have multiple lines. Each one of the line responsibility is to separate one class with the rest of the classes, right? It means we have multiple lines. We have theta 1, we have theta 2, we have so on theta c, where c is the number of classes, right? So theta 1 transpose x will characterize the line that separate the class 1 with the rest of the classes. theta 2 transpose x will characterize the line that separates the second class with the rest of the classes and so forth, right? So now, given a new instance, to classify that to which class this belong to, I need to estimate that what is the probability that this new instance y is equivalent to 1, what is the probability that y is equivalent to 2, and so on, what is the probability that y is equivalent to c, right? So if I have to find out what is the probability of y equivalent to 1, so in the numerator, I should have the weight associated with the class 1, which means e to the power theta 1 transpose c divided by sum over all the e to the power, all the weights e to the power theta c transpose x for all c values, 1 equal to c, c equal to 1 to c. All right. Similarly, can you tell me if I want to know what is the probability of y equivalent to 2? How can I compute that? E to the power
E to the power eta 2
transpose x divided by sum
sigma
over
naught
c
e power theta c
transpose x.
transpose t x.
Simple. Yeah. So this is the cost function. So this is the generalization of the sigmoid function. We call it as a softmax function. So softmax function is the generalization of the sigmoid function. Sigmoid is for the 2 class, softmax is for the multiple class, more than 2 outcomes, right? So this is what the interpretation. This is theta 1, this is theta 1 transpose x, this is theta 2 transpose x, this is theta 3 transpose x. And if suppose probability of y equivalent to 1 is 0.7, probability of y equivalent to 2 is 0.3, probability of y equivalent to 3 is 0.2, 0.1. So which label would you assign? 1 or 2 or 3?
1.
1, because that is maximizing the probability. So we select the class label that maximizes the probability. That's all. So if you have any queries, I can take. Otherwise,
Yes, sir, show that previous slide. Just now, scrolled it. No, before this
Previous.
slide, yes. You wrote something.
Previous. Like
This one only. Sir.
this one only or next slide?
Slide number 24.
24.
The highest probability for the new instance should be considered as that class.
Yeah, select the class label that maximizes the probability. That is here in 25th slide. Take the class label as the most probable label. SC of x. Where C of x is the probability associated with class C. Got it, madam?
Yes, sir. Yes.
So we'll quickly go through the logistic regression model implementation and then wind up the session. Okay. Do you remember 6 steps? Can you tell me?
Yes. Importing the libraries,
Import the required libraries,
load the
load
database,
the data set,
prepare the data
prepare
set,
the data set, split the data set,
yes,
training
prepare
and
the model,
build the model,
evaluate the model.
and then predict and evaluate. Great. So step 1, import all the required libraries. So here we are importing logistic regression model and the evaluation metric is accuracy score. All right. And pandas to read the data set we are importing. Train test split, you know, that to divide the data set into training and testing. All right. The next one is reading the data set. Here I am reading it from the local file, student pass fail data, and the data looks something like this. Self-study daily, tuition monthly, whether the student is passing or failing. Pass means 1, fail means 0. Okay. So now what next? 2 steps are over. What next? Prepare the data set. So there are 3 columns. If I just drop out the last column, I'll get X values all the future vectors. So I'm just dropping out the pass or fail column. I got X. Just access the pass or fail column, I'll get Y. The third step is done, preparing the data set. What next? What next? Fourth step.
Training testing, training, splitting.
Train, test, split, right? So what are the inputs for that? X and Y and the test size, right? So X and Y I'm passing, test size 0.2 I mentioned. If you don't mention anything also, default value is 0.2, right? This returns both the training and testing data. So I've got this, both training and testing data. Now build the model. Logistic regression model I'm calling. I got the model, fit it for the training data, right? So X train and Y train I'm passing for this fit function. So fit it for the training data, predict for the test data. So model.predict I am calling on the test data, and I'm evaluating the accuracy score by passing the ground truth Y test and Y prediction, multiplying it to get in terms of the percentage. So here I've got 66.66. Okay. So because if I execute it different time, no, you may get different results. So now you see that 100%. This is a small data set. That's why results is varying that much, right? Because in the test data, you got 2-3 instances. Okay, even if one of them is wrong, the percentage get down to 66% or 75%. Fine. So now I'll show you how to plot this. Okay. So this is the line equation that you're getting that separates the positive instances from the negative instances. Okay. So if you directly go through the code, you may not understand anything. Let me give some background of it. Okay. So now you have got the points in the 2 dimensions. One dimension is self-study daily. The other dimension is the tuition monthly, right? It means X coordinate is one of the feature 1. Y coordinate is the feature 2. Am I right? Hello? Is that right?
Yes,
Yes, sir.
Yeah. It's taking time. I should have opted for the new board. Okay, by the time it gets open, let us go through the code once, and after demonstration, I'll again run. So here, I'm just creating the line equation means this, you have mx plus c kind of thing, right? So where m is the slope and c is the intercept. So you're deriving the slope and the intercept from this model coefficients and the intercept values, and then using them to create the line equation yd equivalent to m plus xd plus c, right? And then plotting this xd and yd with the red color dotted lines with a line width of 2. All right, and you're filling the space. One above below one you're plotting with the blue color. Above the line you're filling with the orange color. The transparency of 0.2, right? So you can see that this is what the line you're getting. So now how to get this coordinates coefficient values, we'll see. Let me open this. Yeah. Okay, better to open a new board. Okay. So you want to fix a line so that one of the dimension is x1, the other dimension is x2. What is the line equation? Y equivalent to mx plus c, right? Right. So and here the hyperplane that you are actually fitting is theta naught plus theta 1 x1 plus theta 2 x2. Hello, am I right? As there are 2 features. This is the hyperplane, right? But now you want to fit this line in such a way that x2 is the y coordinate. It means you can write it this way: theta 2 x2 is equivalent to minus theta naught minus theta naught minus theta 1 x1. Okay, so what is x2? Minus theta naught by theta 2 minus theta 1 by theta 2 x1. Hello, am I right?
Yes, sir.
Right. So y coordinate is your second dimension x2. So y equivalent to mx plus c. Isn't it in the same form now? x2 equivalent to minus theta naught plus minus theta naught by theta 2 minus theta 1 by theta 2 times x1. Isn't it the same form? Tell me, what is m value here?
Absolutely, sir.
Yeah, what is m value? Minus theta 1 by
Minus
theta
theta
2.
1 theta 2.
What is c value? Minus theta
Minus
naught by
theta 0 plus
theta
theta
2. So the same thing in the code, it is given as a W0, W1 and W2. Instead of theta, there it is given as a theta naught. Okay, that's all. So here you see that. We are accessing model dot intercept, you will get the B value, which is actually in our notation theta naught. Model dot coefficient transpose you are accessing, which is W1, W2. In our notation, it is theta 1 and theta 2. So now compute the intercept, compute the slope. C equivalent to minus theta naught by theta 2, M equivalent to minus theta 1 by theta 2. And substitute that in the equation, yd equivalent to m times xd plus c, and plot that. That's all. You got it. Clear? Go through the code. If you have any queries, you can ask me later also. Yeah, if you have immediate queries.
So y is the predicted value now, sir?
Yes, predicted value.
Sir, in the whiteboard.
Y is the, I mean, here you are plotting for the line equation here. So that it don't, I mean, so here y dimension you are taking here, which is x2. I mean, because x.
Here, sir.
Yeah.
This. But
Yeah.
theta 2 is the feature which we are taking at no, sir.
Theta 2 is the parameter, not the feature.
Okay, sir.
Parameter of the model.
Okay, sir.
See that. Theta naught plus theta 1 x1 plus theta 2 x2. In this x1, x2 are the features. Theta naught, theta 1, theta 2 are the parameters. Parameters of the model.
Okay, sir.
So, just now you told x2 as the target parameter.
No, this is for the line plotting. Like when you see, actually your model is in the 3 dimension. What are the 3 dimensions? X1, x2 and y. Am I right?
Then fine, sir. Then fine.
Yeah, but now you want to show that line in the 2-dimensional space as a separating plane between the points in the 2-dimensional space. Something like this. Okay. A separating hyperplane in the line in the 2-dimensional space. It means one of the dimension is x1 for this, another dimension is x2. It means you want to show this line as x2 equivalent to some m times x1 plus c. So to transform that, we have shown all that derivation and say derived what is m, what is c, and then computed them. Clear, madam?
Yes, sir. Yes.
Yeah. This is for the visualization purpose. This is nothing to do with your learning or whatever. Just to show the visualization, I have derived all that. Okay. Nothing to do with it. It will not affect the learning. Learning is same. Yeah. Is that clear? Shall we move on? Close it.
One
Yeah.
doubt.
Yes, sir, please.
This about that y equal to mx plus c, sir. Here, somewhere else I have read that the c is called as a bias, sir. In this case, y equal to mx plus c.
C is the basically it's an intercept, sir. Right?
Yeah,
Yes,
sir.
bias.
But in case of somewhere else I have read that c is called as your bias. Without c, what will be going on, sir? The line will increase, no? Yes.
You will get the
Question is, your C is called as bias, sir. I think somewhere else I have read that. Is it correct, sir?
yes.
Then,
Intercept or the bias we call it.
yes, sir. Then, I want to know, sir, what is bias actually?
See, sir, like for example,
Hmm.
let me take a very simple example. Let the pattern is something like this in your regression problem. Let's say.
Yes, sir. Yes.
Okay. This is what, let's say this is 0. This is some 3.5. Okay. What is this means? Okay. So this is 3 point. What is the pattern here? Some axis parallel line is the pattern.
Yes, sir.
Okay. So now for what value of, let's say this line equation is y equivalent to mx plus b.
Okay.
So if there is no
Okay.
bias term here, b equivalent to
Ah.
0, it means y equivalent to mx. For what value of m? This will be, this can capture the pattern.
Yes, sir.
It cannot capture that pattern, right? So you take
Yes,
m
sir.
equal to 1. What happens? And x equivalent to 1, this y is equivalent to 1. And x equivalent to y equivalent to 2. Is it
Okay.
capturing the pattern? Not capturing the pattern, right?
Yes, sir. Yes, sir.
Right. So it means what? There is some biasness which can, by adding that biasness, you'll be able to accurately capture the pattern, right? So for
Yes,
example,
okay.
here, when m equal to 0 and b equivalent to 0 0.3.5, this will be able to exactly capture the pattern.
Yes, sir. Yes.
Yeah. So like that. Okay. So, I mean, to make you understand that I've taken m equal to 0, but it can be any positive value also. Okay, it means if the output is deviating with a constant deviation from the mx, then the bias term will be able to capture that part. Okay.
Okay. Okay.
So any other queries?
So last question, sir. Sir, general meaning in machine